Welcome everyone to our Thermochemistry episode, made by special request. Remember, you can always request any video either through our comments or through social media. So this episode is Thermochemistry made easy. We're going to run through some basic concepts and some basic mathematical equations associated with thermochemistry, and it's not going to be as funny or as witty as some of our episodes, because, you know, it's thermochemistry. So first, let's get started with some basic definitions that we want to get out of the way. So first of all, as you probably guessed, thermochemistry is the study of the energy transfer that accompanies a chemical reaction. So it's basically just, thermochemistry. Temperature, however, and heat are often confused with each other, so we want to make sure we make a distinction. Temperature is the average kinetic energy, the average movement energy of the particles in some matter, and it's measured in Kelvin, which is measured in this here. And so we're really measuring the motion of the particles, whereas heat is the energy transferred along a temperature gradient from an area of high temperature to low temperature. So really, heat is what we're talking about, we're transferring energy, whereas temperature is just a measure of an average kinetic energy. So we want to make sure we have that gotten down. A chemistry term that we often use is specific heat, which is a quantity that we use to compare the heat absorption capacity for a material that varies between substances. So this is a known quantity that we can look up in a table, we can really find out experimentally, and it's always associated with a certain substance. And it's usually measured as the amount of energy required to raise the temperature of 1 gram of a substance by 1 Kelvin or by 1 degree Celsius. And the formula for specific heat is this. It's the energy gained or lost over the mass times the change in temperature in degrees Kelvin. And so this specific heat is Cp. The little p means it only occurs at specific pressures. So with each different pressure, we're going to have a different specific heat. This is really a quantity that's unique to each substance that we want to try to find out experimentally. And there's actually certain practice problems that we can do, like this one. So as an example, we have 10 grams of iron that's heated from 300 Kelvin to 320 Kelvin. It absorbs 88 joules of energy in the process. Joules is the scientific term for energy. It's a Newton meter. So we're asked, what is the specific heat of iron? And then next we have, how much energy would 16 grams of iron gain if heated from 291 Kelvin to 333 Kelvin? So in order to find out the second part, we really need to know what the specific heat is, which is what the first part asks us to find. Thankfully, we can use our equation for specific heat, Q over m times delta T, and put 88 joules over 10 grams times 20 Kelvin, and we find that the specific heat of iron is 0.44. We can actually look this up, and you will find that this is in fact the correct specific heat of iron. We can then use this newfound knowledge to find out how much energy in joules as our units would 16 grams of iron gain if heated from this temperature. And when we do so, we can actually rearrange this equation to solve for Q, and upon doing so and using our new numbers, we would find that it gains 295.68 joules of energy. So when we're talking about heat energy, we really needed some way to define it in terms of chemical reactions. And what we can do is we can use something called enthalpy, which is a measure of the amount of heat energy in a system, to do that. So because heat energy is almost always transferred during a reaction, we can look at a change in enthalpy, which is the energy absorbed as heat during a process at constant pressure. So we're talking about a change in enthalpy, this delta H here. We have the enthalpy of the products minus the enthalpy of the reactants is usually how we would look at how the heat energy of a system changes. And when we're looking at a reaction, we're really looking at the enthalpy of a reaction, which is how much heat is being transferred from the reactants to the products. So we can use this, and we can kind of switch gears, but we can use this concept of enthalpy to write thermochemical equations, which you know what a chemical equation is. It's where we write out the different elements and we write out what their states are, and we write out how they react with each other to form a certain product. Well, we can write thermochemical equations to include the absorbed and released energy in our reactions. So, for example, the formation of water from hydrogen and oxygen gas can be written as this as a chemical equation. But we have to remember to include our energy now in kilojoules as our units. When we do so, if we were to double the amount of our moles, let's say we wanted to manipulate this equation to have double the amount of water, we would double our moles as usual to make 4 hydrogen, 2 oxygen, and 4 water, but we also need to double the amount of energy associated with it, because this is a specific amount of energy required to make this transformation, or actually released in this case, released in this transformation, so we need to make sure we have this double the amount of energy released if we double the moles. So the more conventional way you're going to see these equations written is like this, where the above equation is an exothermic equation, we're releasing energy, and this is an endothermic equation. So what's the real difference here? Well, in these equations, we have our chemical equation on the left and our delta H, our change in enthalpy, on the right. What's different, though, is this exothermic equation, our delta H is going to be negative. We're actually losing energy from our system because energy is being released, and you can see in this equation up here that we're losing energy because the products are having some additional energy being given off, so it's exothermic. Whereas in this equation, we need to put energy into the system to make this transformation happen, to put water into our 2 component elements. So we're actually going to reverse the sign here. We're actually going to put energy into the system, and these should be kilojoules, my mistake. We're actually going to put energy into the system to actually absorb energy, and it's going to be an endothermic equation. And so whenever we do this, whenever we change the signs, whenever we change where the products and the reactants are, we always need to make sure we flip the sign accordingly. Just for some clarity here, just to really kind of clear, because exothermic and endothermic, they're kind of similar terms. In exothermic reaction, the products are going to contain less energy than the reactants. If you notice on our slide, we had less energy in the products than we did the reactants. Whereas in an endothermic equation, we're stuffing energy into a reaction, we're actually going to have products that contain more energy than the reactants. So keep that in mind. So when we're talking about this exothermic and endothermic, these are all terms that relate to enthalpy. And so we can actually use different types of enthalpy, such as the molar enthalpy of formation, which this term right here, this delta HF, refers to the change in enthalpy when 1 mole of a compound is formed from its component elements. And we talk about its standard state at 25 degrees Celsius and 1 atmosphere of pressure. This degree sign, sometimes written as a 0, this refers to a compound at its standard state. So why is standard state important? Well, remember how in these thermochemical equations we actually wrote down the states of matter? Well, the state of matter is important because different states of matter have different kinetic energies associated with it, different molecular motion. So we need to make sure we're talking about the standard state at these given conditions. So that's why we're talking about the enthalpy of formation under certain conditions. And when we talk about that, we're really referring to the products of the reaction, what's being formed from certain reactants. So we will see in a few minutes that compounds with a large negative delta HF, and those formed in exothermic reactions where we're giving off energy, we're releasing energy, those tend to be quite stable because they're in a low energy state. Whereas positive delta H values, where we're stuffing energy into an equation, that contains a lot more energy. Those molecules are becoming very unstable because it's storing more energy in this compound. So usually if you see a negative delta H, it's an exothermic reaction and is stable, whereas a positive delta H value is going to be a little less stable. Another type of enthalpy that we can talk about is the enthalpy of combustion, which refers to the change in enthalpy during the complete combustion of 1 mole of a substance. And here, in the presence of oxygen, we're referring to the reactant in this case. So we can actually use Hess's law to find the total change in enthalpy, because sometimes we're going to want to know how does the heat change over a large reaction. We can use Hess's law to know the total change in enthalpy over an entire reaction, because remember that some complex reactions are actually broken down to little mini reactions that occur along the way. Well, those individual changes in enthalpies, if we add them all together, those equal the total change in enthalpy for the larger reaction. So before I get into this example problem, a quick citation. So these next 3 problems are actually found in Holt-McDougall's Modern Chemistry by Houghton Mifflin Harcourt Publishing Company. They're classic chemistry problems that are very useful in our demonstrations, but I wanted to give credit where I actually found the problems. So without further ado, what is the total change in enthalpy for the combustion of nitric oxide, NO, to form nitrogen dioxide, NO2? So this is the equation for the combustion. It's this compound in the presence of oxygen, but we don't know what delta H is. Well, we can actually look at 2 equations that contain all the components we need, NO, O2, and NO2, and we can actually look at their delta H their delta enthalpy of formation. And these will often be either given to us on a test or we can look them up. But these are certain values that we're able to use. Then once we have these values, we can actually go ahead and manipulate these equations similar to the way we might a chemical equation to write the equation in its simplest form that actually gives us everything we need. So what exactly am I talking about? Let's break it down step by step. So we know that NO, nitric oxide, has to be on the reactant side. So we might go ahead and flip that equation to put it there. However, we need to make sure we also flip the sign of our delta H. When we do so, we have correctly nitric oxide on the reactant side. For the second equation, we can leave that as is. So now we have oxygen on the reactants, NO on the reactants, and NO2 on the products. But we still have some stuff left over. Well, thankfully, 1/2 N2s, those both cancel with each other, and 1/2 a mole of O2 is going to cancel with this part on the reactant side, so we can actually add these equations together to get our final reaction over here, which matches the equation above. Then, using Hess's law, we can add our delta HFs together to get our total enthalpy of combustion, which is going to be negative 57 kilojoules. So another quick side note is that the enthalpy of formation is equal to the sum of the enthalpies and the subreactions of those certain molecules. So if you remember, the enthalpy of formation measures the amount of energy in the formation of a certain compound. So if we're looking at the total enthalpy for the formation of pentane from carbon and hydrogen gas, well, what we can do is actually look at different equations that contain those molecules. And so some convenient equations that we have is this first equation with this delta H, the second equation with our H2, and our third equation which has pentane in it. So we have carbon, hydrogen gas, and pentane. So how are we going to get our equation to look the way we want it to? Well, we can use the first two equations that we can actually manipulate the number of moles that we're working with. So if we decide we need 5 carbon, which we do, we can multiply all of the components of this equation by 5. However, we also need to remember to multiply our delta HF by 5 as our new unit of energy. We do the same thing, except we're multiplying it by 6 in this equation. We make sure we account for our energy properly. And then since pentane needs to be on the product side, we're going to do the same thing, except we need to change the sign of our energy. Then simply all we have to do is we cancel out. We have 8 oxygen on this side, 8 oxygen on this side. We have some carbon dioxides we don't need, and some waters we don't need. So we get our final equation as this in our correct substances. And finally, we will get our final equation, delta HF. This should be a gas, by the way. Our delta HF is going to be negative 146.7 kilojoules once we add everything together. And this will be the total enthalpy for the formation of pentane from these two molecules. And all we need to do is track the different types of enthalpies throughout our process. So finally, reactions tend to be exothermic, and you can probably see why. We're losing energy, so our compounds are becoming more stable. They're at a less high energy state and are more stable. However, we sometimes do wonder if we see some spontaneous endothermic reactions occurring, because it can happen in nature. Well, what we need to do is we need to use something called entropy. Entropy is a very broad physical and chemical term, and to break it down here in a simpler way, we can just say it's the degree of randomness or disorder in a chemical system. As disorder increases, as when an object changes state, entropy increases because the molecular motion of the particles becomes much more random. This actually is going to increase the chances of reaction as molecules collide into each other and react. So, using this concept of randomness, how can we predict the degree of whether or not reactions will occur? Well, it turns out we can use something called free energy, and specifically Gibbs free energy, to compare endothermic and exothermic tendencies. So we can actually look at the tendency of an object towards spontaneity, towards natural change, and we can relate enthalpy and entropy in this equation. Delta G at a natural state, our change in Gibbs free energy, which is this new quantity we're working with, is equal to the change in enthalpy minus the temperature in Kelvin times our change in entropy, all of it at its standard state. So okay, that sounds useful, but what does it mean? What does delta G actually do for us? Well, depending on the result we get for delta G, there are certain things that could happen. If delta G is positive, that means we're getting an increase in free energy, and the reaction is not spontaneous. It would not occur in nature if we got positive delta G. However, if delta G is negative, there's a decrease in free energy, and the reaction is actually spontaneous. It will occur naturally with a given conditions. So if delta G is negative, this means that we're getting a tendency where this might be negative and this might be negative, this might be positive, in which case we have a degree of randomness, we have a degree of an exothermic equation that actually makes delta G negative. If delta G is positive, then what we're going to get an endothermic equation that may or may not actually happen. So using these results, and we can use this chart to really predict what's going to happen, but using our delta G, we can predict whether or not an equation will occur naturally. And we can do this with a sample problem. Let's say we have the reaction where ammonium chloride becomes ammonia and hydrochloric acid, And we need to know, does this occur naturally at this temperature, 298.15 Kelvin? And our delta H is 176 kilojoules per mole, and our delta S, our change in entropy, is going to be 0.285 kilojoules per mole Kelvin. So how do we determine if this reaction will occur naturally? Well, we can use the equation we were just given for Gibbs free energy and plug in all of our values. Entropy is positive here, and our delta S is positive, so we may expect something to happen, but it turns out that our change in Gibbs free energy is going to be a positive 91.1 kilograms per mole. Delta G is positive, so this usually indicates that the reaction will not occur naturally at 298.15 Kelvin. This means that at this given condition, this reaction wouldn't occur, but that doesn't mean if, say, we were to increase the temperature, it could happen. It just means that these conditions, we would not see this equation happen spontaneously. And that's basically it for pretty much basic thermochemistry. I know this was a lot in one video, but I hope this was helpful in terms of going over some of the basic concepts and equations that we have in thermochemistry. If this video did help you a bit, then please subscribe and also spread our channel to classmates who might need help. This way we can get our channel name out there, but also so that we can help as many people as we would like to. So thank you very much. Thank you for watching, and have a great day.